Okay, so we have already discussed about histogram manipulation by using linear as well as non-linear functions. Okay, and this is the point operator where we select one DN distal number and process it to a given function, and we generate a distal DN output. Keeping in mind, we are increasing the differences between two nearby distal number, so that when we visualize the image, the difference between a shade of gray color that can be clearly visible. Okay, but when we consider this local operator, okay, so in the local operator, what we do, in addition with the seed pixel that is selected for the modification, we also consider the values of nearby pixels. Okay, so that will do in spatial enhancement, and finally the aim is same, that is to enhance the quality of image as we do in case of histogram manipulation. Additionally, in spatial enhancement, we can able to extract features as well, and we can eliminate the noises which are present in the image. Okay. So before discussing the spatial enhancement, there are certain fundamentals that you need to know, and one of them is spatial frequency. What do we mean by spatial frequency? Like in the frequency domain, you know about the frequency, okay? But in spatial domain, what do we mean by the spatial frequency? Okay. So when we do analysis of images, so we have two domains where we do the processing. The first one is frequency domain. And the second one is spatial domain. Okay. So detail of spatial domain is transformed into the frequency domain by considering the frequencies which are there in the which are present in the image. Okay, they are called as spatial frequencies. Okay, so the spatial frequency filters, also often simply called spatial filters. Okay, they may emphasize or suppress the image data of various spatial frequencies. Okay. So you need to understand what do you mean by spatial frequency, and it can be discussed by considering some example over here. Like two images are given. In the first case, the scene variability is very high, while in the second case, it is a kind of uniform image. This image is containing the uniform detail. It's the grass field, while the first case, it's urban landscape. What happened? Let's say along this line, we are considering the pixels. For simplicity, I'm drawing these pixels in a larger size. Okay, till over here. When you see the see corresponding to each pixel, the objects which are present, you can see when we move if we move along this line, to one point to another point, we can see the sharp change in features. There is building, again in the surrounding of building, we have a grass field, then we have a concrete, then there is a bitumen road, okay, then soil. So along this line, the changes in digital numbers are very fast. Okay. So we can say that due to the scene variability, when we move from one location to another location, there is a frequent change in amplitude of distal number. And it can be portrayed over here, like corresponding to this pixel. If I plot this as a DN number axis, okay, so maybe we have a certain DN number over here. For this, now the nature changes. We have a second DN. Now this is a, if it is rooftop, it all depends. Maybe high reflectance we get. Similarly, the color change. So what we are looking for, like in this way, changes occurs. Okay, so if it's called one direction, 1D, along this axis, okay, we are going across this image, and so if it is represented over here, the 1D information. Similarly, we have infinite lines, infinite directions are there in the image. It is in horizontal direction. We have in vertical direction as well. We have some other directions at a different angle. So there are infinite directions which can be considered over here to analyze the changes in distal numbers along that line. Fine. Mainly in the image, we consider the horizontal direction as well as vertical direction. Okay. So in that case, it becomes directional. Non-directional means all the directions we are considering. Like if theta is represented, so theta is equal to 0, that is slope. It's horizontal. Theta is equal to 90 as well as 270. It's vertical. While for other theta, we have inclined directions. So to define a spatial frequencies in all directions, we just see what is the change in distal number. How frequently the distal number is changing along that particular 1D, one dimension. If the change is very fast, like if you move from one pixel to another pixel, if you can notice very large change, it means the spatial variability in the image is dominant. Okay. And corresponding to these, we generate a spatial frequencies. So, like in this case, if I plot the change over here, the same I'm plotting this axis for better simplicity. So this is the function we are having. Let's say in one particular direction. So let's see. With respect to this particular 1D, one dimension along this line, okay, this DN number is changing very fast. Okay, so you have already learned that how we can convert a given equation into summation of various frequencies. Okay. So the change which we notice over here in the distal number along this direction, that can be represented by summation of sine or cosines. Okay, where this function can be splitted into cos and sine functions with a varying amplitude. We write it a sine theta, a sine, we can say a sine n theta. It can be written in one. A sine n omega t. Okay, so using n omega, different frequency components are there. They are summed up to realize this function. Okay, but if the variability is this function is highly variable in terms of its value, in terms of its digital number value corresponding to uh, change in 1D from one location to another location. So at very high frequency, if is high, the amplitude A naught will be high. So at high frequency, if scene variability is very large, so at a high frequency, we get large amplitude A naught. It means the high frequency components are dominant. High spatial frequency components are dominant in case of a high scene variability. Fine. And, and it is very evident over here, like very frequent changes can be represented by high frequency component. Okay. So corresponding to that frequency value, the amplitude A naught will be high because ultimately amplitude A naught is representing this overall magnitude of digital number. Now let's say in case of low scene variability, if we have a uniform features, like in this case, it's grass field, what you will have? Nearly constant, no change. So in this case, for a high frequency value, A naught will be very less. And for low frequency value, A naught will be dominant. Okay. So in this case, the low spatial frequency components are dominant. So I hope now you have understood the meaning of spatial frequencies. Spatial frequency represent the variability in the scene. Okay, the high spatial frequencies, if they are dominant, it means scene variability is more. While in case of low scene variability, the low spatial frequencies are dominant. So overall, spatial frequency is a kind of representation of roughness in the variation of digital numbers. Okay, so image is more rough in terms of variation if you can notice the changes in the digital number along a particular direction. In high spatial frequency areas, the DN values may change abruptly over a relatively small number of pixels, like across the road, if you are crossing the road, field boundaries, shore lines, etc. So we can say that uh, at the edges or at the junction line where there is a transition from one particular feature to another, the change in DN number is more abrupt. Like for example, we have a water body over here, and just at the shore line we have a tree. Okay, and we are using NIR band to map this. You know that in NIR band water completely absorbed. So one pixel we are getting from water, and just next to it another pixel is from the tree. What will happen? For the water pixel, let's say DN could be 5, while for the tree pixels, it will be 230. Because vegetation reflect more. Highest reflectance we get in NIR. So just see the abrupt change, 5 to 230. So there is a kind of edge we can see in the image, and that edge is represented by high spatial frequency components. Why it is so? Because when we move from one pixel location to another, there is an abrupt change. So the smooth image area, like in this case, this can be called as a smooth image. So in smooth image areas are characterized by low spatial frequency. As you see in this graph, you can't see a very abrupt change. It's a kind of uniform, no change in the digital number along the various lines. So corresponding to very low spatial frequency. Just see, if there is no variation, means very low frequency, low change. So corresponding to low frequency, we have a dominant amplitude A naught that represent the low spatial frequencies. Various frequencies, the sine and cosine functions are combined together to realize this function. Okay, but when you analyze component one by one, so the component at low frequency has a dominant A naught. It means overall the low frequency component is dominant. So smooth image area are characterized by low spatial frequency where DN values only change gradually over a large number of pixels, like homogeneous agriculture fields or water bodies. Now, if we are interested in highlight one particular type of features, like we want to highlight the uniformity or uniform features in the image, then how it can be done? Let's say we are interested in to see only the boundaries. Only we are interested to see the abrupt change from one feature to another. Boundaries are the location where one particular type of object is changing to another type. So there we have a boundary like road, and if we move away from road to the pedestrian. Okay, so road is concrete while road is bitumen, while concrete become pedestrian become concrete. So there could be a kind of boundary, and that you can notice in the image. Similarly, we have other boundaries across which the nature of objects changes. Okay. For that case, we need to use
सर
high pass filter. Mhm.
सर लास्ट में जो सर वो इससे पहले सर वो सिटी और ग्रास का मैप आपने बताया था सर, वहां पे एक बार फ्रीक्वेंसी और एम्पलीट्यूड का एक बार से फिर से कंक्लूजन बता दी.
Okay, over here,
यस.
I hope all of you are aware about Fourier series and Fourier transform.
यस सर, यस सर.
What we do in Fourier series? If let's say a particular function is given, so what Fourier series say once you apply it in that particular function? बताइए, आपसे ही पूछा हूं मैं.
यस. Fourier
So
series.
in generalized way, non-sine and cosine functions can be represented by combination of many components of combination of sine and cosine functions at a different frequency. Correct?
Yes.
Let's say we have a periodic and non-periodic functions. Periodic and non-periodic non-sine and cosine functions, they are represented by combination of cosine functions at a different frequency. Fine.
Yes, sir.
Now, if the input the input function that we are going to split into various components of sine functions. If in the input component, the variation is very fast. Like in this case, if you see the first case, if you move along this direction, and if you notice that very sharp change in the values, distal number values, or it can say it's y value. Okay, if it is the change is very fast, and if you break it into sine and cosine part, so in that case, in case of large change, you can see what you are doing. Just you are going by using this
Yes,
Then
sir.
we have one other variable. Then this. So they are combination of sine and cosine components at a different frequency. So to represent a very sharp change, what will be required? We the high frequency components amplitude will be high.
High
Let's
frequency component amplitude. Okay, sir.
let me explain it in a better way. I was expecting like at least these concepts should be clear to you. Okay. Anyway, just see. If I start from here, uh, and this is one direction. Let's say I'm considering x corresponding to, so theta is using the reference direction. Theta is equal to 0. Okay. What do you notice in this case? When you are moving along theta, moving along x-axis over here, from one pixel to another pixel, there uh, there are a significant difference. Okay, so that
Yes,
significant
sir.
difference tells us like due to the high scene variability. Okay,
Hmm.
due to the high scene variability, we can notice the differences in high differences in crystal numbers when we move along any direction. Okay, and
Yes.
that difference, the magnitude of distal numbers are represented over here, and let's say this is the difference delta. While for the next 2 pixels, this is the difference, and then next 2 pixels, this is the difference. But difference are dominant. This particular this function can be represented by combination of sinusoids at a different frequency. Let's say I calculate average of distal numbers. Okay. Now around the average, we see what is the variation. Two functions I am plotting. Just tell me which function is uh, more representative compared to other. This is one sinusoid and another sinusoid I am plotting over. In case of sinusoid at a different frequency, they are actually a representation of variation in the image. This is the function f1, and this for this sinusoid I am saying f2. So compare with f1 and f2, which one is closely representing the variation in the input in DN input curve, f1 or f2?
Sir, F1.
Why f1?
because it represents
Just
various number of frequencies.
see very carefully. Just see the transit very frequent. I mean, once you are moving from one location to another location, you can notice the change in digital number, and that is depicted over here. Which particular sinusoid is closely representing this variation? This is F1 and this is F2. Which one is more closely representing?
Oh, yes, sir. F2, F2.
So F2 is more closely representing this variation in the DN input. Okay. So what we do, see, I'm just discussing the concept of Fourier series over here, and that is expected, all of you know it. So these are the kind of prerequisite for this course. Some basic concept of Fourier series, some basic mathematical concept. But anyway, if F2 is more closely representing this change compared to F1, then how you can reduce the weightage of F1? F1 weightage, if it is represented by, let's say, A1 sine, it's a 2 pi F1t. And the first one, it is represented by A2 sine 2 pi F2t. If you want to reduce, because F1 is not closely representing, it's not in case of F1, the sinusoid component corresponding to frequency F1, to reduce its effect, because it's not a close representation of this variation, what you should do, you should decrease the A1. Okay. And though F2 is a closely representing this change, so you can increase the A2. So effect, this will be highlighted and this will be reduced. So for all the frequencies corresponding to which this amplitude of this component is large, okay, they are termed as a dominant component over here. So in case of high scene variability, F2 is a low frequency, sorry, F2 is a high frequency over here. So the high frequency components are dominant because they are closely representing the variation in the scene. So spatial variation in the scene in terms of difference in digital numbers are closely represented by spatial frequencies at high values, at their high values. Is it clear now?
Yes, sir.
Okay. Similarly, in the same way, we can discuss this part over here. When you plot it, okay. Now we take the average. This is the reference line. Now just tell me, for this particular function, which frequency component is closely representing it? Okay. Which one is closely representing this variation?
The second one with
F1 and same nomenclature, this F2. This second one.
F. Yes,
So
yes.
now in this case, A1 value will increase while A2 will decrease to 0. Okay. Because the sinusoid with low frequency values are the close representation of this variation. Okay. So this is then why this is why we say that in homogeneous image, Okay, where you can notice a gradual change in the distal numbers along various directions. The low spatial frequency components are dominant. So low spatial frequency F1, I'm just splitting this statement. Low spatial frequency is F1, as you see in the image, and they are dominant, means corresponding to this F1 in the sinusoid, the A1, that is amplitude, dominant means this will increase. Okay, so A1 will increase, and what is the representation if A2 is decreases and A1 is increases? So how you can represent it? Just see what does it mean. It means, let's say if your very A2 value is close to 0, so for that F2 frequency, this is like amplitude is very less, no? So this is the function for F2, and this is for F1. Why it is so? Because this amplitude A2 and this is amplitude A1. A1 is very large compared to A2 because the low frequency component is dominant. Is it okay?
Yes, sir. Thank you, sir.
You're welcome. So I hope the contents which we have covered, all the contents are clear to you. And in the next lecture, we'll discuss about various filters that we use as for spatial enhancement of images.